Welcome to this tutorial. I would be solving question number 8 of paper 2-1 October-November season 2017 in this tutorial, and the topic of this question is nuclear physics. We would be having some questions and the testing of the concepts of half-life and the three radiations in this question. So the question says a sample of radioactive isotope radon-222 decays by the emission of alpha particles. As alpha particles travel through air, the air is ionized. The first thing they are asking us, describe the composition of an alpha particle. So we know that alpha particles are like helium nuclei, and they are composed of two protons and two neutrons. So the composition of an alpha particle is there are two protons and two neutrons joined together in an alpha particle. In the next part, they are saying explain how an alpha particle ionizes air. Since alpha particles are positively charged, and because of this they make the air molecules lose their valence shell electrons, so the atoms of air or the molecules of the air ionize and alpha particles are able to gain some electron. In the third part, the question says state how the relative ionizing effect of alpha particles compared with that of beta particle. So the ionization effect of alpha particle is stronger as compared to beta particle, and when we compare the ionization effect of alpha particle with respect to gamma particle or gamma rays, still the alpha particles have a stronger ionizing effect because of having a larger amount of charge. In the next part, the question says the half-life of radon 222 is 3.3 10 raised to 5 seconds. So here we are provided with the value of the half-life of radon 222. The number of radon 222 atoms in the sample is 4.8 10 raised to 4. So in a sample this much atoms are present, 4.8 into 10 raised to 4. Determine the time that it takes for the number of radon 222 atoms in this sample to decrease to this number, 1.5 10 raised to 3. Now, since the starting number for the radon atoms is 10 raised to 4.8, 10 raised to 4, so when a half-life passes, the remaining radioactive particles would be this number divided by 2. And when another half-life passes, we would be again dividing it by 2 when the third half-life passes, and this division would continue until the number we reach becomes 1.5 10 raised to 3 particles. So instead of writing 2 multiple times, I'm writing 2 raised to n here, and we need to find by how much division we get the answer equal to 1.5 10 raised to 3. Now this n here represents the number of half-life which would be required in this case for this much particles, 4.8 10 raised to 4, to decrease to this number. Now if we try to find the value of n here, 4.8 into 10 raised to 4 would get divided by 1.5 into 10 raised to 3, and the answer should be equal to 2 raised to n. In the next step, the division gives us the answer of 32, which is equal to 2 raised to n. If I convert 32 with the base of 2, the power would be equal to 5, and here the value of n that we get would be equal to 5. So it means 5 half-lives would be required in this case to convert the starting number of radioactive substance to this number, which is 1.5 10 raised to 3. Now, how much time would be required? The time could be calculated when we multiply this n with the half-life. So 5 would get multiplied by the value of the half-life, which is 3.3 10 raised to 5, and we get 1.65 into 10 raised to 6 seconds. And if I write it in standard form, so it would become 1.7 10 raised to 6 second. So the required time is 1.7 into 10 raised to 6 seconds for this part. Okay, in the last part, the question says suggest one reason why in practice the time for the number of radon 222 atoms to decrease to this number may differ slightly from the value obtained in the previous part, which is part B1. Now, the reason for the slight difference is that radioactive emission is a random process. So the time could differ slightly. So I'm writing the reason that radioactive emission, since it does not follow any pattern, so it is a random process. There could be a slight difference in the observed value